Well, hello. As we had kind of led into in class the other day, today we're going to talk about electric potential. And what that really means is potential energy dealing with electricity. So electric potential is not a lot different than anything else we've already been discussing, except we're now going to go into start talking about potential energy or electric potential. Our objectives in this is we want to be able to distinguish between electric potential energy, electric potential, and potential difference. We want to be able to solve problems involving electrical energy and potential difference. We want to be able to describe the energy conversions that occur in a battery. If we get that far, that'll be something we discuss more in class. Well, what I want you to understand is that the electrical potential energy, that is the potential energy from electricity or charge, is potential energy associated with a charge due to its position in an electric field. And let's say then, for example, I had an electric field. Obviously, as we've discussed, the field will be traveling in this direction from the positive to the negative. So that's the direction of our field. If we take, in this case, some charge, let's just take a positive test charge, we can put it at different positions. And at different positions, it's going to have different electrical potential energy. And what I want you to understand is it's going to change according to where it's at in this field. So over here, if I go clear to the far right, the electrical potential energy here is going to be much less because it's already very close to the negative. That's like saying if we had the Earth, I'll draw a green Earth here, green effect, green Earth, and if you, actually let's just draw Earth like ground, here I'll erase that, start over here with that again. Let's talk about Earth, so we got the ground, and if I take a brick and place it here, it's got a certain amount of potential energy. But if I take that same brick and lift it higher, its potential energy increases because it's farther from where it wants to go. It's the same way with the electrical charge. The farther we take it from where it wants to go, the more electrical potential energy it's going to have. So, an example of this is we have these three spots here, A, B, and C. The electrical potential energy is greatest at A because it's the farthest from where it wants to go, over above this electron. The electrical potential energy is a component of mechanical energy. So we've got all these components down here: internal energy, kinetic energy, potential energy of gravity, potential energy of elastic, and now we're going to include potential energy of electricity. Here is what I was trying to get you to understand on day 5 in class when we were trying to draw that potential energy is similar to work, or is work. We can say that potential energy, because they're both measured in joules, so they're both energy, they're both work. Well, because of that, we can say then that potential energy is equal to negative force times distance. Negative just means the distance. Well, force we know then is Q times E, so the potential energy of electricity, or electric potential energy, is negative Q times E times D, meaning it's going to act in the opposite direction that it was heading. So as we were saying here, the electrical potential equals the work that must be formed against electric forces to move a charge from a reference point to the point in question divided by the charge. So earlier we were talking about the electric potential energy, as we're saying here, the electric potential energy. Now we've gone on and we're talking about the electric potential. Electric potential is different. Electrical potential energy is potential energy due to electricity. But the electric potential, as you can see down here, is the voltage, and the electric potential is related to potential energy. So electric potential is the voltage. The electric potential associated with the charge is the electrical energy. All right, that's this up here, the electrical energy divided by the charge. So that's what we're talking about here. So now, let's keep going on this. Potential difference. It's electrical potential difference or potential difference is the same. Potential, the word potential here tells us that we're dealing with voltage. So potential difference can be reread as voltage difference, which makes sense because we're talking about delta here. It's the change in the voltage, the change in the electrical potential energy divided by the electric charge. So we have three things. We have potential energy due to electricity. We have the potential, the voltage, the voltage due to electricity. And we have the potential difference, which is the difference in the voltages between two different locations. And that the potential difference is how much energy change is there according to where we put the charge. If you go back, and I'm going to draw my little chart up here again, we have these two charges. The potential difference is the change in the potential energy between two different locations. And what we're really talking about here is we've got this test charge at these two different locations, and we know that the electric field is going to the right here. So there is a potential difference between these two locations. A has much more potential energy than what B does, and that would be this change right here. The potential difference is a uniform field varies with the displacement from a reference point. Potential difference in a uniform electric field, meaning the electric field's not going to change. So what this really means, again, I'm going to go back to my picture. So I've got my field here. We take this test charge and we put it in here. We've got these two different locations. Let's call this A and B. What I want you to understand is the potential difference is what is the change, potential difference. The change in the voltage, and that's what this triangle here, is related to the change in potential energy. If we take this charge and put it at point A, it's got more potential energy. Let's say this, for example, would be 100 joules. At B, it might only have 10 joules. Well, what's that change? It's a 90 joule change. It would be divided by the charge of that test charge. How much charge does it have? So the change would be 90 joules divided by some answer, which would be in coulombs. So voltage, the change in the voltage would be 90, in this case, 90 joules divided by something. If we look at this and break it down to the next one here, the potential energy, as we said, is negative QED. The charge is Q, so the voltage, the change, the potential difference, the change in the voltage is in the opposite direction of the electric field times the distance that we moved it. So, the voltage is in the opposite direction, so in this case it's to the left. It's times the electric field, so whatever the quantity of the electric field is, and the distance that it's been moved. Alright, we got a sample problem right here. First of all, I'm going to make my list. Alright, I've got this it's 2 centimeters. So my distance is going to be 0.02 meters. I just automatically changed it into meters. But as the electric field has a magnitude of 215 newtons per coulomb, and as the charge moves, its electrical potential energy decreases by 6.9 times 10 to the negative 19th. Find the charge on the moving particle. So I'm going to do this first part here. I know that potential energy is equal to negative QED. So I'm going to plug in what I know, 6.9 times 10 to the negative 19th is equal to negative Q times 215 times 0.02. Well, after I work this out, I find out that the charge is equal to negative 1.6 times 10 to the negative 19th coulombs. Well, what that tells me then, sorry, I had some technical difficulties. What that tells me, though, is that my charge signifies that this is an electron. So it's negative 1.6 times 10 to the negative 19th. So that is the charge that they put in here. The next thing here says, what is the potential difference between the two locations? So now, I'm going to use my equation for that, for potential difference. Now the change in voltage, or the potential difference, is equal to the change in potential energy over the charge that we just found. Well, when I plug in the information that we've already got, we find out that there is a change in voltage of 4.3 volts between these two locations. If you go back and look at my example here, between the two locations that we originally had it and now have it, there is a change in voltage there of 4.3 volts. Here's another problem. Oh, I'm sorry, this is the same problem. Okay, what I want you to do for tomorrow is you've got that section there, 2 sections there for you to write your story problems. This should be easy for you to come up with some questions. In those story problems there, what I want you to write is I want you to include in there all of the equations that we have now that deal with either charge, potential energy, potential difference, force, the electric field. Let's get them all written in there, and then we'll talk about these tomorrow. Hey, you have a great evening. I'll see you on the flip side.